Good evening, everyone. I hope you have had an interesting day so far with a lot of sharing of various use cases and dimensions of the big data and various examples of how it's implemented in real-life systems and predictive analysis. I am not going to redefine what big data is. Everybody can use their own interpretations of what big data is. It's a loaded term, and people use it in different ways. I am here to speak, primarily share a particular dimension of big data, which Mike was alluding to, is to the big velocity, the data that comes at you fast. And I'm going to speak not just about the data that comes at you fast, but precisely about how you act on that fast data in a very fast time. So it's not just about seeing the data or reading the data from the fire hose and to a point of analytics and displaying it on dashboards, but what you do with it. How fast can you respond to that big data coming at you and take some concrete actions from a systems and engineering perspective. And hence, the topic is diagnostics, predictive analysis, which eventually would lead into self-healing systems. And I'm going to talk a little bit about self-healing systems at the end, which is a dangerous term. It could set you up for failure also if it's not set right. So a little context about what we talk about. Big data is a tool and not a solution. I mean, there are debates in the industry about even is tooling more important, as the people, the human intelligence behind big data is more important, and I mean, we can have those debates. But the point is, it's a tool, and how you apply the big data gives you a solution in the big data space. And large amount of data without any context to it can even be dangerous. And if the element of human intelligence and sentiments and context is not added to it. One story that comes to my mind to talk about this specific aspect of big data comes from the Harvard University professor Gary King. He's director of Institute of Quantitative Social Sciences. And there was a big data project that was executed, and it was attempting to predict the US unemployment based on the feeds from the various social forums like Twitter, like other blogs, like other things. And they focused on certain keywords like jobs, unemployment, classified. So they picked few terms, and they wanted to correlate and see how, and applied a term in analytics called sentiment analysis, and try to establish a correlation between the number of or the frequency in these terms which are being used in these blogs from the millions and billions of the tweets and blogs that are coming up, and see if there is a correlation between US unemployment on a monthly basis. They collected tons of data from that perspective. And one finding is that at a particular period in the year, they saw a huge spike in usage or tweeting of a particular term they were using, huge spike. And they were like really surprised. Wow, that means US unemployment rate is going to change or increase very high. They kept waiting, and nothing happened. That unemployment rate did not increase. So the point here is that they forgot, or they failed to notice that Steve Jobs died that year, at that point in time. And that Jobs was one of the keywords they were searching for, right? So they tried to correlate, and they saw, oh, the US unemployment should go high, but it didn't. So it's funny, but at the same time, it tells you the dangers that are lurking out there if we don't apply the right human intelligence and right context in big data and try to do right things. And that becomes even more and more dangerous if you build things which I'm talking about as self-healing systems. Because if you do one wrong thing, and it can bring down your whole system, and it can take millions and millions of dollars from your sites like we operate, like Macy's, eBay, Amazon.com. These are all high traffic sites and have special profiles of high traffic coming in the morning, day, and during the week there are different patterns, and during the year, like the Black Friday and those kind of seasons, a very different profile of these systems exist. So now going further into this thing. So I think I owe an explanation of why this traffic map. The traffic map is like if we travel from one place to another, I do at least look from a traffic pattern as to how much time will it take for me to go there. It gives me the patterns of what's green, what's yellow, and what's red. And that got me thinking like a few years back as how can I build a predictive system in my enterprise systems where things like these big sites, they look simple. You go and buy stuff on that, right? But there are hundreds of components that are orchestrating together or choreographed together to deliver that customer experience, which the millions of customers experience. So in that case, it comes very handy if you are able to build something like that based on predictive analysis, that I am able to see various layers of my architecture and see in a predictive analytical way where things are going, what my customers may experience after 20 seconds, 1 second, or whatever that time period is. So, and I'm going to speak more about, this is more of dashboarding and reporting, then what can you do to actually take some automated steps and corrective actions. So how to get there? So we don't have a lot of time. I can get into a lot of details of technically how to build these things, but I'll take a high-level approach of steps, simple steps of how to get there. So the first and important step here is data generation and transport. And when I say data generation, it's not just simply creating data and throwing it on fanning it out and then doing some analytics on it. Creating precise and accurate data is the key to it. In the retail space or all these e-commerce websites, I think we are very good at building the analytics from a customer experience perspective, like tagging of core metrics or RAM, which is real user monitoring, those things, and that are fed into the traditional analytics systems or big data systems like Hadoop, and then we pull weekly, monthly, and annual reports about what's going on there, how is the customer behavior going on, when my orders count went down, what was going on there. But not many of the people tie it to what is happening inside the systems. What is happening inside my Java virtual machine? What is happening inside my 27 different components that are working together to deliver that experience? So this aspect talks about the data generation from that precision perspective. Now, it's an oversimplified diagram. So if you see, I've tried to represent multiple layers of the architecture, and this is not even the enough number of layers. There are multiple more layers than these shown here. But the point is to able to instrument your code. Let your code speak, because I always tell people that code doesn't lie. So if you make your code speak at the right time with right precision, you can get a lot of data. So the point here is you have to provide, and which we did in my current and the past job, that we came up with a framework for our developers. Developers can code in a very different way. They may log in a different way. We created a framework which was given to our developers when they start building applications or services. And they don't have to worry about instrumentation of their code to that level. It's already instrumented. That instrumentation already exists. They just worry about writing the business logic and instrumenting the code at a more micro level, like a particular transactions have to be logged. So you can use various mechanisms doing it. I'm not going to go into details about what different mechanisms can be used. We use logging for this, and we did a lot of log frameworks were used to instrument code at different layers, the services at different layers, and they were fanned out to a log aggregation, local log aggregation at the JVM level. You can use various types of technologies there too, like the Glue technology used by LinkedIn. It's a pretty good open source tool. There are other open source tools you can Google and you'll find it. So I'm not going to go and list all those things to you guys. You can also build your own Java component, your custom component that's sitting in your JVM and collecting all this log coming from the log appenders and putting it there. So that's the part of the data generation aspect of it. And then the key here is, again, this would still be big data, millions and millions of records generated, events generated every hour. But it's not going to make sense unless you are able to build a correlation logic at what happens at different layers of your architecture. And hence, the concept called globally unique identifiers. So what you do in your n-layer architecture, starting from layer 1 where the transactions start, you generate a global unique identifier. And what you do is you traverse that global unique identifier throughout the layers. While each layer is operating on its own and fanning out the data, yet you are able to get the correlation IDs so that you can trace a particular transaction starting from layer 1 all the way to the mainframes or JDBC drivers or wherever that transaction is going. So that's the data generation aspect of it. And then you put it out on a message bus. Again, that's a very generic term I've used. Now, given the fast and the speed of the data, traditional message buses like JMS implementation of TIBCO and those things, they may not come handy for this type of fast acting on the data. So in those cases, you can use open source things. I'm a fan of open source technology, so like Flume. Flume agent, some of you might have heard. So you can use Flume technology to be able to collect this data, aggregate it, and put it to a log consumers and your log aggregators. In the diagram, you can also see something called CMDB, and people call it with different names. But I want to highlight the importance of a CMDB in this ecosystem. It's configuration management database. It could be sitting on a graph database or a traditional database. But the aspect it contains, it's a storehouse of the entire environment. For example, your services, your product, your category, your checkout, all those services that are working together. It contains the map of those, where each of these services is hosted, what is the cluster, where is the location, what data center, is it running on JBoss, Tomcat, all that aspects of your services are mapped into this configuration management database. And this database or storehouse is primarily updated by your solutions that are making changes in your environment, like your platform as a service or infrastructure as service, your deployment and provisioning systems. Rest all the systems heavily use it, but more for lookups to do their operations. So till this point, if you see, it's still traditional reporting that you get this data, you can put it into analytics infrastructure like Hadoop and run MapReduce jobs, Hive, and then report it through dashboards, reports, different consumers of these reports. So it's still big data, it's still precise data, it's coming at you fast, but you're not acting on it fast. This is still traditional reporting till this point. Now, you can fork the data which you are collecting through Flume to a more real-time processing engine. And I think Mike was alluding to the CP, and the death of CPs is going to come. But it's irrespective of whether CPs are going to die or not. But something in that line which is going to give you that function is needed that reads this data more from a aggregated data analysis that's done on the log aggregator is fanned out to this real event processing engine, right? And this engine is able to create patterns of the different events. For example, a service that is invoked, a get product category service, how many times it's invoked. It has an SLA, a service level agreement, for example, 20 milliseconds. Now, you want to do something if that SLA is breached multiple times for a period of time. For example, you can say if my SLA is breached from 20 milliseconds to 30 milliseconds for over a period of 15 seconds or 10 seconds, I got to do something. That's the pattern that's built in this event processing system. And this is one example. Every company, every organization, engineering organization may have their own different SLAs and different use cases they want to do it. This is just one example of how a pattern can be built in this real event processing system. Once this pattern is built, you can take it further ahead and feed it into a diagnostic systems. Again, solutions are available. You can build your own in-house Java or C-based diagnostic systems, or you can buy something from the market. But the point here is this diagnostic systems takes these patterns, and then you imply certain actions on it, right? What do you want to do? What is the diagnostics of a certain pattern coming? So if pattern number 1, 2, and 3 are matching, this is what is primarily happening inside the systems. So that's the kind of thing which you can do not automatically, but through human intelligence. So your heroes of service operations, your heroes of site operations, and your architects and stuff, they are going to tell you the nature and the construct of a service and what a particular pattern, if we leverage, could result to, or what could be the manifestation of a problem, what problem can be seen in that case. So this I'm showing in one slide, and if we try to build it in a one big bang, I think we are setting up ourselves for failure. So the key is to build the plumbing slowly and then start building these diagnostics use cases based on the human intelligence, the people and the experts you have in your company or your organization telling you what needs to be built. And you build this by, first of all, getting the diagnostics done manually. And once those diagnostics are hitting the 100% accuracy mark, then you automate them, putting in the diagnostic engine and test your diagnostic engine that if this 20 times this thing happened and these patterns matched, the manifestation of the problem or the root cause analysis, was it right or wrong? One example in this case is going back to the service we talked about, product category service. If its SLA is missed for a particular period of time by these many milliseconds, that could mean multiple things for different engineering organizations. For some, it could say that my service is responding slow. and hence I need more capacity. It could also mean that within my service cluster, a few nodes have gone down, right? And that is causing the capacity. For some, it's a Black Friday scenario, and my cluster is getting overwhelmed by the lot of traffic I'm receiving. So different analysis of this type of pattern needs to be done in the diagnostics, and it varies from company to company and the type of service you are building here. What happens next in this case is once you have those rules identified, now if you see on the left side, there is called out PaaS and IaaS that I was referring to earlier. So platform as a service and infrastructure as a service, hoping that you have something in place in your company which allows you to automatically provision systems. And again, it ties back to the concept of the cloud and virtualization. And if you are able to provision your systems automatically, there are two aspects to it. One is provisioning, that is the hardware or the virtual machines, and then deploying JBoss, Tomcat, or whatever container you're using, and then deploying your code. And every organization has a different style of doing it. Some have templated VMs, and all they do is they clone the VMs when they have to add more additional capacity. Some layer software after another, and depending on how much time they want to put in to build a particular service. So the reason I'm explaining these details is that if once you have mastered the root cause analysis in the diagnostic system through the pattern analysis that's coming and fed into you from your event processing system, then you can automate the capacity or corrective actions through the PaaS and IaaS APIs. How you do it is what I was referring to earlier. If your diagnostic system says that the capacity of this server or this cluster is going down, and as a corrective action, a team has agreed, a corrective action in this case would be to add 20% more capacity to a cluster, then you can invoke a control API on this PaaS and IaaS system and say, give a token, a service token. For example, it's a product service. So you give a product service token to this diagnostic systems, and this diagnostic system is going to go and look up in the CMDB and identify the whereabouts of this service, how many nodes in a cluster, what is it sitting off, what does it need to be built, and then depending on what provisioning and deployment mechanism you're using, you're going to have the PaaS and IaaS API look up the CMDB and then go deploy those nodes on the cluster. Basically, what we call flex up and flex down. So it could flex up the capacity of the cluster. In some cases, certain nodes have gone bad, and the corrective action may not be just adding 2 or 4 nodes, but the corrective action could be to take off few nodes from the cluster and then add more capacity. And there are load balancers to which these clusters are generally tied. You can go to the load balancers, remove the ECV check, and then get the traffic removed from those nodes, add further nodes. So these are just 2-3 simple examples of the corrective actions. Depending on how complex your systems are, and depending on how much you want to automate slowly, you can build various use cases, their root cause analysis, pattern matching, and eventually doing some corrective action and self-healing. As I said in the beginning, self-healing itself is a dangerous term, and some companies have miserably failed while trying to build a system. If you do it too early without maturing your processes, without having the right expertise in-house, and you start doing it, then you may take wrong actions because your analysis coming out of your big data may not be accurate, and you may bring down certain nodes in a cluster or remove certain nodes or do something which may have a negative impact on that. Now, the key here is going back to the map which we talked about earlier, is this, that at least with the right amount of analysis and diagnostics, you can have the map or the dashboard ready for your people, DevOps and other engineers, who can take these corrective actions manually. So how do you make sure that the actions which you are taking are right or are accurate? First, you do them manually. When you see a pattern match and you get a root cause analysis, you allow somebody on that support team to take an action from your portal, whatever that control API or control portal is you guys are having in the company, and you say, okay, go expand or flex up and flex down the capacity of the servers, or take that corrective action. When you repeatedly do it a number of times successfully, then you've established a corrective action that is fail-proof or is 98, 97% accurate. And then you automate it in your diagnostic systems through the PaaS and API. So you don't jump onto that and we tried doing that. We tried to establish some of these patterns. And of course, the goal is not to go 100% automated. The goal is, even if you are able to automate 50 to 60% of the corrective actions, what you have done is you have created a lot of efficiency, operational efficiency in your organization, and your experts who are, I'm not sure how many people are involved in the production crisis or when there are incidents happening. There are 30, 40 engineers from all over the globe dialing into a conference call, and then people looking for some smart heroes who can tell you what's going wrong, and then there is finger pointing. It's not my service. I think the problem is coming with the front end, from the back end, from this service and that service. A lot of time is spent, and especially for mission critical, from a dollar value perspective of systems being down, like eBay, like Amazon stuff. Even for minutes, if the systems are down, you're losing millions, you're bleeding millions and millions of dollars. So the impact is huge. And if you can automate and if you can generate such type of predictive analysis, you will save tons of money and tons of time and resources. Even if you don't go automated and you stop at the point of diagnostics and building this kind of the map I'm talking about, traffic map, so that your 60% work is done. But if you're smart enough and you try slowly and iterate through your build out, you can even lead to automated cleanup or corrective actions as well. So what's in it for me? I think I did cover some of these parts, but why would somebody build such a system? And it's about predictive troubleshooting, as I said, not depending on the tribal knowledge of few engineers you got in your team, and if they're not available, gone on vacation to Hawaii, then you're kind of basically hosed. You will have to call them or have somebody else and say, hey guys, can you talk about it? And they say, this guy knows it, and he's been doing it for 3 years or 7 years. And that's a big help in predictive troubleshooting. Financially smart. So we don't have to build the church for the Easter, right? And this is a typical problem. I think my retail brethren will acknowledge this, that because we are usually built for those Black Friday peaks and stuff, and we are still working towards leveraging the virtualization and cloud. But this aspect is, we leave 80 to 90% of our capacity unused throughout the year. And there are few companies who are able to repurpose throughout the year certain things, but not very, very effective in doing that. But if you work in that model, in this kind of diagnostics and predictive analysis model, you don't have to build the church for the Easter. You run your systems at the capacity you want to run for a period of time, for certain months. And when you need burst capacity, you use your this analysis for capacity planning. And then for a particular month, to November, December, or whenever your prime time is, you do use the burst capacity either in a public cloud or a private cloud. And if you're using the right level of cloud APIs like OpenStack and stuff, you can pretty much go to any provider and use the burst capacity to do it. Of course, there are PCI and legal issues in terms of what data could be stored. And as I said, time is not enough, and we can go into each of these dimension and talk an hour about it and have a debate. But the point is, of course, you're not going to put, again, the goal is not to put 100% of your systems out in public clouds. The goal is to leverage only the commodity, the things which are not very, very sensitive, not HTTPS traffic. Your customer data may still reside inside your data centers, but something which is not going to get lost from a confidentiality perspective can be hosted. That burst capacity can be used for that. I think we already talked about the live in cloud and where it makes sense. So that's the aspect of it. Then accurate and real-time correlated state of business and systems. In the beginning, I talked about generally we are good at instrumenting the business analysis side of things on the Hadoops and provide these reports. But once you have this type of engineering instrumentation in your code and in your systems and services, and they're all working as a big ecosystem, then you can tie your business analytics to your system analytics, including CPU, memory, and the SLAs and the time spent by services, and do a lot more good for your business. Because you sometimes wonder why the traffic is going wrong, and there are predictions about, hey, look at the market, did we plan it right? Is our merchandise fine? What's going on? Is the traffic going to some other provider and stuff? But if you sometimes things are within our systems, and if we have a deeper dive into our systems, then we can find out what's going on in the system. It's getting a real health check of your systems, and then you can correlate the events happening from a customer end to what's happening inside your own house, inside your JVMs, inside your services. I talked about operational efficiency. I think that basically overall gives you that operational efficiency. I think I kind of covered, and I know I had a tough job because this was followed by dinner, or is followed by dinner. It's tough to beat a dinner, so I didn't want to keep it going for a long period of time. So if you guys have any questions, feel free to ask.
Yasir, excellent talk. Thank you. What you've described here is a state of art in the commercial industry in organizations like yours, and I've seen many of these, and most of them are not as good as what you just described. My question is, what do you see next? What do you need from the research community or from the engineers and the smart people in this kind of room here to take you to the next step where you'd like to be 5 years from now?
I think it's, I mean, there are many things we need from the engineers and from the community. I think accuracy and precision is the key. We are still not there from an accuracy, and I think Mike was talking about the algo part of it and the different algorithms that are running and the speed of those algorithms. So we are, what I talked about, I won't call it real-time feedback. It's still near real-time, and again, near real-time is also up to interpretation. That, is it milliseconds, is it microseconds and stuff? So I think the faster we can get at this data and do precise calculations and get back with the right pattern matching and stuff on this data is, I think, the key to this, for the success of this type of self-healing system. I think that comes to my mind as the immediate thing. They would definitely, and we can talk over dinner, something more. And I also have to be careful as like representing Macy's here. I don't want to go into too many details from a implementation perspective, so I have to watch out for that as well.
Any other questions? All right.
I think everybody's hungry, yeah.
Yeah, thank you very much, Dan.
Thanks.